Multiplication of matrices. Welcome to today's lesson on the multiplication of matrices. Let's begin with an introduction to the concept. First, it is important to understand that matrix multiplication is a fundamental binary operation within the field of linear algebra. In simple terms, this means it is a primary mathematical method used to combine two matrices to produce a new one. Now, you may recall how we perform matrix addition, where we simply add the corresponding elements in the same positions. However, matrix multiplication is quite different and involves a more complex process. Instead of a direct element-to-element calculation, it requires us to combine the rows of the first matrix with the columns of the second matrix. As we move through the following slides, we will discuss the specific conditions required for this operation to be possible and walk through the step-by-step mechanics of the row-by-column rule. The condition for multiplication, compatibility. Now that we have established that matrix multiplication is a more complex process than simple addition, we must address a critical prerequisite. Before you attempt to multiply two matrices, you must first determine if the operation is mathematically defined. It is important to understand that, unlike addition, matrix multiplication is not always possible. This leads us to what I call the golden rule of matrix multiplication. The product of two matrices, A and B, denoted as a B, is defined if and only if the number of columns in the first matrix, A, is exactly equal to the number of rows in the second matrix, B. To visualize this, let's look at the dimensions. If matrix A has dimensions m by n, where m represents the rows and n represents the columns, and matrix B has dimensions n by p, where n represents the rows and p represents the columns, we can see that the inner dimensions, which are both n, match. Because these inner dimensions are identical, the multiplication is possible. Finally, we need to determine the size of our answer. The resulting matrix, which we will call matrix C, will have dimensions derived from the outer numbers. Specifically, if matrix A is m by n and matrix B is n by p, the product matrix C will be of the order m by p. Once you have verified that the matrices are compatible and you know the dimensions of the resulting matrix, you are ready to move on to the actual mechanics of the calculation, which we will discuss in the next slide. The mechanics of multiplication, the row-by-column rule. To find a specific element in the resulting matrix C, which we denote as the element in the ith row and kth column, you must calculate the dot product of the ith row of the first matrix, A, and the kth column of the second matrix, B. To make this easier to visualize, let's break this down into a clear step-by-step process. First, select the ith row from matrix A second, select the kth column from matrix B third, multiply the first element of that row by the first element of that column. Fourth, multiply the second element of the row by the second element of the column. You continue this pairing process for all remaining elements in that specific row and column. Finally, you sum all these individual products together. This final sum is the value that goes into the ith row and kth column of your result matrix. If we express this using a mathematical formula, assuming matrix A has dimensions m by n and matrix B has dimensions n by p, the element C sub ik is calculated by adding the product of a sub I1 and B sub 1k, plus a sub I2 and B sub 2k, and so on, all the way to a sub in and B sub nk in formal mathematical notation. This is written as the summation from j equals 1 to n of a sub ij multiplied by B sub jk. Now that we have established how to check if two matrices are compatible for multiplication, let's move on to the actual mechanics of the process. This is governed by what we call the row-by-column rule. While this formula might look intimidating at first, it is simply a shorthand way of describing the step-by-step process we just covered. In the next few slides, we will apply these mechanics to a real-world scenario and a numerical example to see exactly how this works in practice. Real-world example, calculating total cost. Now that we have discussed the theoretical mechanics and the row-by-column rule, let us apply these concepts to a real-world scenario to understand how matrix multiplication is used to organize and process data. Imagine a bakery that sells two types of items, cakes and cookies, across two different locations, which we will call Shop 1 and Shop 2. First, let us look at matrix A, which represents the quantities sold. This is a 2x2 matrix where the rows represent the shops and the columns represent the items. Specifically, the first row shows that Shop 1 sold 10 cakes and 50 cookies, while the second row shows that Shop 2 sold 20 cakes and 30 cookies. Next, we have matrix B, which represents the price per item. This is a 2x1 matrix. The first element is the price of a cake, which is $200, and the second element is the price of a cookie, which is $10. Our goal is to calculate the total revenue for each shop. Before we proceed with the math, let us apply the golden rule of compatibility that we learned in slide 2. Matrix A is a 2x2 matrix, and matrix B is a 2x1 matrix. Because the number of columns in matrix A matches the number of rows in matrix B, both being 2, the multiplication is mathematically defined. Furthermore, the resulting matrix, which we will call matrix C, will take the outer dimensions, making it a 2x1 matrix. Let us now perform the step-by-step calculation using the row-by-column method. To find the revenue for Shop 1, we take the first row of matrix A and multiply it by the first column of matrix B. This means we calculate 10 times 200 plus 50 times 10. This gives us 2,000 plus 500, resulting in a total of $2,500. Similarly, for Shop 2, we take the second row of matrix A and multiply it by the first column of matrix B. We calculate 20 times 200 plus 30 times 10. This equals 4,000 plus 300, giving us a total of $4,300. Finally, we place these results into our resulting matrix. See, this is a 2x1 matrix, where the first element is 2,500, and the second element is 4,300. This example demonstrates how matrix multiplication allows us to calculate multiple totals simultaneously. Now that we have seen a practical application, let us move to the next slide for a purely numerical walkthrough to ensure you are comfortable with the arithmetic. Numerical example walkthrough. Now that we have seen how matrix multiplication applies to a real-world scenario, let us walk through a purely numerical example to solidify the mechanics of the process. Let us consider two matrices, matrix A and matrix B. Matrix A has the first row as 1 and 2, and the second row as 3 and 4. Matrix B has the first row as 5 and 6, and the second row as 7 and 8. Step 1 is to check the dimensions, as we discussed in our earlier slides. Matrix A is a 2x2 matrix, and matrix B is also a 2x2 matrix. Because the number of columns in matrix A equals the number of rows in matrix B, both being 2, the inner dimensions match, and the multiplication is mathematically defined. As a result, our product, matrix C, will also be a 2x2 matrix. Now, let us apply the row-by-column rule to find the individual elements of matrix C. In step 2, we calculate the element in the first row and first column, which we call C11. To do this, we take the first row of matrix A and the first column of matrix B. We multiply 1 by 5 and 2 by 7, then sum these products. This gives us 5 plus 14, which equals 19. In step 3, we find the element in the first row and second column, C12. We use the first row of matrix A and the second column of matrix B. Multiplying 1 by 6 and 2 by 8 gives us 6 plus 16, resulting in 22. Moving to the second row of our result in step 4, we calculate C21. Here, we take the second row of matrix A and the first column of matrix B. We multiply 3 by 5 and 4 by 7, which gives us 15 plus 28, equaling 43. Finally, in step 5, we find the element in the second row and second column, C22. We use the second row of matrix A and the second column of matrix B. Multiplying 3 by 6 and 4 by 8 gives us 18 plus 32, which equals 50. Our final result is matrix C, a 2x2 matrix where the first row consists of 19 and 22, and the second row consists of 43 and 50. Please ensure you are comfortable with this step-by-step process, as we will now move on to the key takeaways and some common mistakes to avoid. Key takeaways. Now that we have walked through both a real-world scenario and a numerical example, let us summarize the key takeaways to ensure you have a solid grasp of the concept before we move on. First, let's revisit compatibility. As we discussed earlier, the multiplication of matrix A and matrix B is only possible if the number of columns in matrix A is exactly equal to the number of rows in matrix B. If this condition is not met, the operation is simply not defined. Second, regarding the size of the resulting matrix. If matrix A has dimensions m by n and matrix A has dimensions n by p, the resulting matrix C will take the dimensions of the outer numbers, which is m by p. Third, remember the core operation. The process always follows the row by column rule. You multiply the corresponding elements of a row from the first matrix by the elements of a column from the second matrix, and then you sum those individual products together to find a single element of the new matrix. Finally, it is crucial to understand that order matters. Unlike the multiplication of simple numbers, matrix multiplication is generally not commutative. This means that matrix A multiplied by matrix B is not the same as matrix B multiplied by matrix A in many cases. Reversing the order might even make the multiplication impossible due to the compatibility rules we just mentioned. Keep these 4 points in mind, as they will help you avoid the common pitfalls we are about to discuss in the final slide. Common mistakes to avoid. Now that we have covered the mechanics and seen some examples, let's wrap up by discussing some common mistakes to avoid so you can ensure your calculations are accurate. First, be careful not to perform element-wise multiplication. When we first started this lesson, we saw that matrix addition is simple because we just add corresponding elements. It is a common mistake for beginners to try and do the same with multiplication by multiplying elements in the same position. However, as we have learned, matrix multiplication is not element-wise. It is a more complex process. Second, never ignore the dimensions of your matrices. Before you begin any calculations, always refer back to the golden rule we discussed in the second slide. If the number of columns in the first matrix does not equal the number of rows in the second, the matrices are incompatible, and the multiplication is mathematically undefined. Always check your dimensions first to save yourself from unnecessary work. Third, be mindful of the order of operations. A frequent error is attempting to multiply a column of matrix A by a row of matrix B. Please remember the row by column rule. You must always use the row from the first matrix and the column from the second matrix. Switching these will lead to an incorrect result or a dimension mismatch. Finally, watch out for basic calculation errors, specifically forgetting to sum the products. As we saw in our bakery example and the numerical walkthrough, finding a single element in the resulting matrix requires multiple multiplications. Ensure that you complete the addition of all those individual products before moving on to calculate the next element.